Hello everyone. In this video, we'll understand about various terminologies being used in graph theory. The very first one is adjacent and incident vertices. Consider this graph. It's an undirected graph. In this graph, this vertices 1 and 2, and then 1 and 3, 1 and 4, 2 and 3 are all adjacent vertices. In general, we can say vertices I and j are adjacent if and only if I comma j is an edge in the graph. In this graph, edge 1, 2, this edge 1, 2 is incident on the vertices 1 and 2, and also edge 2, 3, this one is incident on the vertices 2 and 3. In general, we can say edge ij is incident on the vertices I and j. Now consider this digraph, means it's a directed graph where you may notice that there is a direction from 1 to 2, 2 to 3, 4 to 3 also, 3 to 4 also, 3 to 5 also, 5 to 4 also. Here we say vertex 2, this one is adjacent from vertex 1, and vertex 1 is adjacent to vertex 2. Edge 1, 2, that means this 1, 2 is, it is directed. So you write 1, 2, you don't write 2, 1. 1, 2, 1, 2 is incident from vertex 1 and incident to vertex 2. Similarly, vertex 4, if you look into, it is both adjacent to and from 3, because there is an arrow from here to here, from here to here. So you say vertex 4 is both adjacent to and from 3. And then edge 3, 4 means this edge we are talking about, 3, 4 is incident from 3 and incident to 4. So that is what is about adjacent and incident vertices. Then we say in general, directed edge I comma j is incident to j and incident from I. And vertex I is adjacent to j and vertex j is adjacent from I. Then the next terminology is loop. We also call loop as self-loop. It is an edge that connects a vertex to itself. Consider this graph 1, 2, 3, 4. It is a directed graph 1 to 2, 2 to 3, 3 to 4, 1 to 4. And there is a loop here at vertex 3. So that is called as self-loop. An edge of a graph which starts and ends at the same vertex is called a loop. In the below graph, edge from 3 to 3 denotes a loop. Then next terminology is degree of a vertex. In an undirected graph G like this, the degree of a vertex V is determined by counting number of edges incident on that vertex. Let us consider each of the vertex and see what is the degree of it. If I consider vertex 1, the number of edges incident on this vertex is 1 is this, 1 is this, that means degree is 2. If you consider 2, 1 is this, 1 is this, so degree is 2. If you consider 3, 1 is this, another one is this, third one is this, that means degree is 3. And for 4, degree is 2 because there is one connecting here, one connecting here. And if you consider 5, only 1 degree because there is only one edge which is getting connected. If the degree of a vertex is even, for example, here, 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 then the vertex is called an even vertex. And if the degree is odd, here there are two places, one is this, one is this, we call those two vertices as odd vertices. All right. Then the degree of a graph is the largest, I mean, till now we saw degree of the vertex. Now we are talking about degree of a graph. Degree of a graph is the largest degree of the vertex in that graph. So in this example, the largest degree is 3. So the degree of the graph is 3 for this particular example. Then comes minimum and maximum degree. For a graph, capital G, which is denoted by V comma E within brackets, minimum of all the degrees of the vertices, which is nothing but minimum of degree Vi, such that Vi element of the vertex set V be denoted by small delta of G. And similarly, maximum of all the degrees of the vertices, which we call it as max of degree Vi. Here we should, this one is denoted by capital delta of G, which I didn't write it. Maximum of all the degrees of the vertices is maximum of degree of Vi, such that Vi is an element of the vertex at P, that is denoted by capital delta of G. Then next coming is the handshaking lemma. Lemma means it's like a theorem. The sum of the degrees of the vertices of a graph is equal to twice the number of edges. That is, summation of all the vertices, degree of all the vertices is 2 times cardinal number of the set E. Means how many, set E means edges. So the number of edges, how many are there, multiplied by 2, you get the total number of degrees of all the vertices added together in a graph, where this n denotes the number of vertices and this cardinal number of E is nothing but the number of edges. For example, consider this graph 1, 2, 3, 4, 5. Here we already, we will see vertex for vertex 1 degree is 2 because there is one edge here, one edge here. For 2, one edge here, one edge here. For 3, 1 here, 1 here, 1 here, 3. 4, 2 are there. 5, only 1 is there. Now, if I add all these degrees, 2 plus 2, 4, 4 plus 3, 7, 7 plus 3, 10. And even we may look into the number of edges. There are 5 edges, 1, 2, 3, 4, 5. So cardinal number of set E is 5 only. So we can see very clearly that the degree, which is 10, is twice of 5. So it is summation of degree Vi is twice of. This is based on this lemma, and we just considered one example. Now let us understand the proof of this handshaking lemma. Degree of a vertex is nothing but the number of edges incident with that vertex. Every edge is incident with exactly 2 vertices. So far in all the diagrams we saw this, every edge is incident with exactly 2 vertices. So every edge gets counted twice, once at each end. So sum of the degrees counts the total number of times an edge is incident with the vertex. That is why this, hence the proof you can say, because that is why summation of all degrees is equal to 2 times of number of edges. Let us now see indegree and outdegree. In a directed graph like this, the number of edges originating from a vertex, for example, from 1 to edges are originating. One is this 1 to 2, another one is 1 to 4. That is called outdegree of that particular vertex. And the number of edges entering the vertex means, for example, if you consider vertex 1, none of the edges is entering that. That means the indegree of 1 is 0. So that is called as indegree. Now for all the vertices, let us calculate the indegree and outdegree. For 1, we already saw it is 0. And for 2, if you look into indegree means how many arrows are coming in? This one, and this one. That means it is 3. For vertex 3, one is this, another one is this. That means it is 2. For 4, one is 3 to 4, one is 1 to 4. So it is 2. Outdegree of 1. From 1, 2 edges are originating. One is going to 1 to 2, another one is going to 1 to 4. So it is 2. For vertex 2, one is going from 2 to 3. Only one only. Then for vertex 3, you may notice 3 to 2 there is an arrow going, and 3 to 4 there is an arrow going. So it is 2. And for 4, one is 4 to 3, another one is 4 to 2. So it is 2. So that is what is about indegree and outdegree. Next comes isolated vertex. A vertex of degree 0 in a graph is called an isolated vertex. An isolated vertex in a graph has no edges incident with it. Consider this graph. You may notice all these vertices are connected actually with some sort of edges, whereas this one, it doesn't have any edges at all. This vertex, we call it as an isolated vertex because its degree is 0. Now, next one, pendant vertex. Let G be a graph. A vertex V of G is called a pendant vertex if and only if V has degree 1. In the below graph, vertices 1 and 4 are pendant vertices. You may notice for 1, only one edge is getting connected, and for 4 also only one edge is getting connected, whereas for 2, there are 2 edges, whereas for 3, there are 2 edges. That is why 1 and 4 are called as pendant vertices. Next is order of a graph. If capital G, which is a graph, finite graph, denoted as V comma E, then the number of vertices denoted by the cardinal number of set V is called the order of G. So in this diagram, if you look into the number of vertices, there are 6 vertices, 1, 2, 3, 4, 5, 6. So order of this graph is 6, right? Size of the graph means it is about the number of edges. Again, looking into the same diagram or the graph, you may notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 edges in this. So that is denoted by cardinal number of set E, and that is called as size of the graph. So one is order of the graphs means number of vertices. Size of the graph means number of edges. So hence the cardinality of the edges at E of G is called the size of the G. So for the above graph, the size of the graph is, for the above graph, the size is 10. Next comes degree sequence of a graph. Let G be a graph with vertices V1, V2 and so on up to Vn as the vertex set, and let Di is equal to degree of vertex Vi, then the sequence D1, D2 and so on up to Dn in any order is called the degree of sequence G. The vertices of a graph G are ordered so that the degree sequence is monotonically increasing, so that your small delta of G less than or equal to, which is nothing but D1, and that should be less than or equal to D2, less than or equal to D, and so on, less than or equal to Dn, which is nothing but capital delta of G. This is the least degree, this is the highest degree of a particular graph. Let us understand about walk in a graph. See, the walk is a sequence of vertices and edges of a graph. If we traverse a graph, then we get a walk. Note that both vertex and edge can be repeated in a walk. For a graph G, a walk is defined as a sequence of alternating vertices and edges. For example, V0, then after that edge 1, then vertex 1, edge 2, vertex 2, edge 3, vertex 3, like that it keeps on going, then edge K and then vertex K. Each edge EI is nothing but Vi minus 1 comma Vi. The length of this walk is the number of edges passed in that walk. So here you may notice E1, E2 and so on up to Ek. That means the length of this walk is K. Consider this example, a graph having 5 vertices A, B, C, D, and then A to B there is an edge, B to C there is an edge, C to D there is an edge, D to E there is an edge, and then C to E also there is an edge, and B to D also there is an edge. So here A, B, C, D, and then B is a walk. Here the edges are not repeating, even though vertex is repeating B and B, but edges are not repeating. It's called as a walk. But it is not necessary that edges should not be repeating. Here, next example, even edges are repeating, right? Because you may notice AB is there, BC is there, then CD is there, and then DC, it is going back, and then CB. See, BC and CB are actually the same edges, so edges are repeating. Of course, the vertices are also repeating. You may notice BB has come, CC has come 3 times, like that. So both of them can be called as walk. Now, what is an open walk? What is a closed walk? A walk is said to be an open walk if the starting and ending vertices are different. That is, the origin vertex and the ending vertex are different. What do we mean by a closed walk? A walk is said to be a closed walk if the starting and ending vertices are the same. Means if a walk starts and ends at the same vertex. Let us consider this example 1, 2, 3, 4, 5. It's a graph. Here 1 to 2, and then 2 to 3, and then 3 to 4, then 4 to 5, and then 5 to 3. So here the starting vertex or ending vertex are different. So it is an open walk. Whereas in the next example, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 3, then 3 to 1. You may notice here the start vertex and end vertex are the same. You call this as a closed walk. What do we mean by trial? It is an open walk, right? in which no edge is repeated, but vertex can be repeated. Since it is an open walk, the starting vertex and ending vertex should be different. No edge is repeated, but vertex can, no edge is repeated, but vertex can repeat. So you may see here 1 to 2, 2 to 3, 3 to 5, 5 to 4, and 4 to 3, right? Vertex is repeated 3 and 3, but none of the edge is repeating. It is called as a trail. Then path. A open walk in which no vertex and edge appears more than once is called a simple path or a path. Consider this graph here, 2, and then I'm walking, I'm going with in a path 2, after that E1, then 1, then E3, then 4, then E7, then 5, then E6, then 3 is a simple path of length 4. Why length 4? Because it is passing through 4 edges, 1, 2, 3, 4. That is why you say this path's length is 4. Then let us see what is circuit. A circuit is a path that begins and ends at the same vertex. See here, it starts with 1 and ends with 1. Inside the path, there may be repeat of vertices, but edge will not be repeated in circuit, right? So here, 1 to 3, 3 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. None of the edge is getting repeated, but it is starting with a vertex which is 1 and ending with the same vertex. We call it as a circuit. What do you mean by cycle? Cycle is nothing but a circuit, but that doesn't repeat vertices. Except, sorry, I wrote here wrongly, except for the start and end vertex is called a cycle. So in this graph, you may notice 1, this is 1, 2, 1 after that 3, and then 6, and then 5, then 4, and then 2, and then 1. Even though here start and end are same, like a circuit, here also it start and end are same, but here the 3 is getting repeated, that vertex. Here nothing is getting repeated inside, right? That is called as cycle. So these are the various terminologies which are being used in graph theory. In case if you find the contents of this video to be useful to you, I request you to please like it, share it with your friends, and also subscribe to my channel. Thank you.